Good morning. I am Dr. K. DHANALAKSHMI, working as a professor in the Department of Computer Science and Engineering, and today I am going to deliver a lecture on virtual memory, which is one of the important concepts of operating system. This virtual memory covers demand paging, page replacement and thrashing. So we are going to discuss about these three topics here. We will discuss all these three topics one by one. Before moving to virtual memory, let me brief about memory, how process executions are performed by the operating system in memory. So I'll explain that, then we'll move to virtual memory concepts. So in general, there are two types of memory everyone might know: primary storage memory and secondary storage memory. Primary storage memory is also called physical memory or RAM or volatile memory. Then secondary storage memory is like hard disk, pen drive, CD, then DVDs, etc. So generally all our programs, applications, files are stored in secondary storage memory initially, and whenever we want to execute a file or open a file or access a data, that file should be loaded into the physical memory, then it can be executed. So from the secondary storage memory itself, that files cannot be executed. So they should be loaded into the physical memory, then they can be executed. So that loading process can be done by the operating system, and generally in the secondary storage memory, all the programs are stored, and that space is called logical address space, and the address referred by the user for that program is called, or for that file is called, logical address. But when we load that program into physical memory, they are referred by using the address called physical address, and the memory in which the processes are stored are called physical memory address. But generally that physical memory address is not same as logical memory address. So that secondary storage memory data are stored into the physical memory in some other location. So address of logical memory and physical memory are different. So that operating system is responsible for translating that logical address into physical address. So secondary storage memory addresses are called logical address. So our programs are we know only that logical address, and during that execution of process or program, they are loaded into the physical memory. At that time they are called physical address, or that files are referred by using physical address. Then what is paging, and how that processes or files are loaded from secondary storage device to physical memory. So they can be loaded by using one of the concept called paging. So here that logical memory or our program is divided into fixed blocks, fixed same size blocks called pages, and that physical memory, it is divided into fixed same size blocks or partitions called frames. So here that logical memory addresses or logical memory programs are divided into fixed size blocks called pages, and that physical memory is divided into equal partitions called frames. Here when we want to execute a program, that pages should from the secondary storage memory should be loaded into the physical memory frames, and then for every program there is a separate page table. So separate page table is maintained to keep track of the frame number. That is, here suppose let us assume this program or process is having 4 pages starting from 0 to 3, and its respective page table is available here. In this page table, that a page number is used as an index, and it is generally having 2 entries, but the first entry is used to specify frame number, that is page number 0 is loaded into that frame number 1. So that frame number is specifying the frame number in which, or the frame in which that particular page is loaded into the physical memory. So by maintaining this frame number, that operating system can easily convert or calculate that physical address, or can easily locate where that particular page is available in the physical memory. And then nowadays all operating systems are supporting for multitasking. So at a time the users can execute more than one process. So generally they are executing n number of processes at a time. They will try to execute n number of processes. That is, they may open many applications at a time. So all the applications opened or accessed by the user should be first before loaded into the loaded into the physical memory before starting the execution. But that physical memory address is smaller than that secondary storage, physical memory size is smaller than the secondary storage memory size, and sometimes even one application size is larger than that physical memory. So it is not possible to load all the opened or all the currently executing process into physical memory, but that operating system is doing that. Instead of loading the complete program or complete file into the physical memory, it is loading only a partial or part of the program into the physical memory. So whenever a particular portion is necessary, that portion can be loaded into the physical memory. So here that multitasking is possible, or more than one applications are executed by the operating system by loading only a part of the applications into the physical memory frames. So this can be done by using the concept of virtual memory. So virtual memory, so virtual means that literal meaning is imaginary. There is no memory like that, but it is an illusion. So it is creating an illusion that our users are utilizing, our users are thinking that their whole or complete applications are available or residing in physical memory. So that virtual memory is a very important or one of the feature of operating system that allows the execution of processes which are not completely available in memory. And also that virtual memory concept or this feature compensates the shortage of main memory by transferring the data or applications between the secondary storage device and main memory. So that is that virtual memory illusion is specified here. This is called secondary storage device, or we can say backing store. This backing store, that is what are all the processes are ready for execution, first loaded into this backing store. So they are loaded in terms of pages. Every application or every file is divided into different pages. So all the pages will be stored in that backing store. So that backing store is a fast accessing associate memory. And then this is our physical memory. That physical memory is divided into different frames, and then actually that processes are loaded from the backing store into physical memory, and a particular page is not required or not necessary. It may be swapped out to the physical memory. But here that virtual memory, it is providing an illusion that the complete application or a complete application is residing in physical memory. So it is an illusion, but really it is not happening like that. But anyway, all the currently executing processes are available in physical memory. So that virtual memory can be implemented by using one of the concept called demand paging. So we can implement the virtual memory by using demand paging. A page is bring into the physical memory only when it is needed. So bring a page into the memory only when it is needed. So it is called demand paging. What is the advantages of demand paging? Demand paging, it required less I/O operations, and then it required very less memory, because at a time all the complete program is, the whole program is not loaded into the physical memory. They are loaded into the physical memory in terms of pages whenever they are required, and then they are providing faster response, and it is supporting for more number of users to execute their process. And then, okay, so how that and that demand paging is also the part of operating system. So operating system is responsible for loading the pages into the from the secondary storage device to physical memory. So it has to handle all that page fault. So whenever a page is required, that program will send a request to the operating system. This page is not available in physical memory, so I need that page. So that operating system will refer whether that page is valid page or not. If that page is valid, then it will take necessary steps to then it will check whether that page is available in physical memory. If it is not available, then it will take necessary steps to bring that page into the physical memory. If that page is not a valid page, then that operating system will abort that operation. Okay, so how that operating system can understand whether the particular page is available inside in physical memory or not. I already told you about that page table. For every process is divided into set of pages, and for every process there will be a separate page table. The page table is having two entries. One is frame number and another one is valid invalid bit. So that valid invalid bit is maintaining 1 bit information. It may have either 0 or 1. If that page is available in physical memory, then its respective bit, valid invalid bit is set to 1. If the page is not available in physical memory, then its respective bit is set to 0. So if a page is not available in physical memory, then its respective page valid invalid bit is set to 0. So by using that we can easily identify that. If a page is not available in the physical memory, then that program will send a request to the operating system as a to bring that page into the physical memory, and this is called page fault. If a page is not available in physical memory, then it will raise the message called page fault. So that page fault can be handled by the operating system. So this is an example given here for that is, this one shows some of the pages are available in physical memory and some of the pages are available in secondary storage device. So let us assume this is a program, this is a file containing 8 pages from 0 to 7, 8 pages, and for this a separate page table is maintained, and here in physical memory some of the pages, that is 3 pages, A, C and F are already available in physical memory. So A, C, F, their respective A, C, F, 0, then 2, page number 5. So their respective bit values are valid, invalid bit values are set to valid, and then the remaining pages are available in only in secondary storage device. So their respective valid, invalid bit is set to invalid. That means that page is not available in physical memory. Okay, so if page fault is occurred, how operating system is handling that? So that is, operating system has to take necessary steps to bring that pages or bring that page into the physical memory. So what are the steps are followed by the operating system? So diagrammatically that is given here. This is a program executing at present. Suppose that program want to access the instruction called load M. Okay, if that load M, so if that this particular page is not available, means that the program will check whether that page is available or in physical memory or not by tracing page table. So if it is not available, then that program will immediately send a trap message to the operating system. First it will try to refer this page. If that page is not available in page table, it is send a trap message to the operating system. That is, it is send page fault message to the operating system. So that operating system has to bring that page into the physical memory. So first that operating system will check whether that page is a valid page or not. If it is a valid page, then it will check that page whether it is available in backing store. Okay, if it is available, then it find free frame from the physical memory and bring that page from the secondary storage device to free frame. That is, it will copy that page into the free frame, and then once that page is loaded into the physical memory, immediately its respective page table valid invalid bit is set to valid, because now it is that particular page is available in physical memory, and then that program will restart its execution as usual. So in this way, that page fault is handled by the operating system. So if page fault is occurred, operating system has to take necessary steps to bring that page from the secondary storage to our backing store to physical memory. Okay, so here in this case, if free frame is available in the physical memory, no problem. It will identify a free frame, and that required page will be loaded into that free frame. If that free frame is not available in the physical memory, what will happen? So in that time, so there is no free frame in the physical memory. So at that time, that operating system will go for replacement. That is page replacement. So among all the frames are filled with some pages. So among that pages, which page should be taken for replacement? So selecting a page for replacement is called victim page. So that page replacement is happened, that is that operating system will do that page replacement. So before finding the page for replacement, it has to check what is the priority of the page, and whether that page is already used or not, whether it will be referred in future. So it has to consider lot of constraints. So first it has to find some page in memory, but it not really in use. So if there is a page like that, then swap it out, and then in that particular frame load the new page. So here that page replacement is performed by using different page replacement algorithms. So in this paging, demand paging, there are different page replacement algorithms. First one is first in first out, then optimal page replacement algorithm, and then least recently used approximation algorithms, and then counting based algorithms. So these algorithms are used for page replacement, that is selecting a victim page, select a page which is going to be replaced. So that is called victim page. So if there is a set of algorithm, definitely we have to evaluate the performance of the algorithm. So the performance of the algorithm is measured, is calculated by finding the number of page faults. An algorithm with the minimum number of page fault is considered as the best algorithm. So here let us discuss these algorithms one by one with a example. So here in this example, I am going to consider this example for explaining these algorithms. This example is called reference string. This reference string is having numbers. These numbers are representing page numbers. So here let us assume there is a file that is containing 5 pages. 1 to 5 pages are there, and let us assume that processes are that particular file is executed in this order, so that it will be accessing that pages in this order. So I will explain that algorithm by using this example one by one. So I am going to explain these algorithms with this example. The first algorithm is first in first out. The page is replaced, the order in which they are arrived or they are entered into the physical memory. So let us consider this string for FIFO, first in first out. The strings are 1 2 3 4, then 1 2 5 1 2 3 4 5. So a program is having 5 pages, that all that 5 pages are accessed in this particular order during its execution. So let us assume for this particular program or for this particular process, the memory allocated or the number of frames allocated is 3. Number of frames allocated is 3. So number of frames allocated is 3. So by using only the 3 frames, this process has to complete its execution. So initially, so 3 frames are there. So initially, this particular process execution will be started, and this will try to access page 1. So page 1 will not be available in physical memory. So it is send a page fault. So once that page fault is occurred, then that 1 is loaded into the physical memory here. 1. So frame numbers 1, 2, 3. So here, and second time that it will try to access page number 2. So page number 2 is not available here. So that operating system will bring that page into the physical memory. It will load that page into the second frame. Then it will try to access third page. Third page is not available here. So it will bring that page, and that will be loaded into frame number 3. Then next it is trying to access page number 4. So page number 4 is not available here, but that allocated frames are only 3. So among these 3, it has to select one page for replacement. So which one is the victim page? So in FIFO, first in first out, the page which is entered into the frame first will be replaced first. So among these 3 frames or these 3 pages, page 1 is entered first, loaded into the physical memory first. So page 1 is selected as a victim page, and that will be replaced with 4. And then next page it is going to access is 1. So again 1 is not available here. So it has to go for page replacement. So here among these 3, the first page entered is 2. So 2 is selected as a victim page. So 2 is replaced with 1. And then next page is it is going to access is 2. So 2 is again not available here. So go for page replacement. So this is the first entered page among that 3. So this is the victim page. Here that 2 is loaded. Already 4 and 1 are available here. And then next it is going to access page number 5. Page number 5 is not available here. So it will be moving for page replacement. So among these 3 pages, page number 4 is entered first. So 4 is selected as a victim page, and 4 is replaced with 5. 1 and 2 are already there. And then next it is going to access 1. 1 is already there, so there is no page replacement. And next it is accessing 2. 2 is also available here, so it will try directly access that page. And then 3, it wants to access 3. 3 is not available here, so it has to select a victim page. So among these 3 pages, the page first entered is 1. So 1 is selected as a victim page. So here 5, then 1 is replaced with 3, and then 2, and then 2. And next page it wants to access is 4. 4 is not available here. So among these 3, the first entered page is 2. 2. So 2 is replaced with 4. 4. And next page is it is going to access is 5. 5 is already there. So here we have to, in each and every algorithm, we have to find the number of page faults. So first page fault, then second one, third, fourth, fifth, 6, 7, 8, 9. So totally 9 page faults are occurred. So for this FIFO algorithm, totally 9 page faults are occurred. But in general, if the number of frames are increased or the number of frames allotted for a particular application or a particular program is increased, definitely the number of page faults will become reduced. So that the graph will be like this. The graph will be like this. So here that number of frames will be there. Number of frames will be represented here. and here that number of page faults. So if the number of page frames are increased, definitely number of page faults are decreased. So the graph will be generally like this. For more number of frames will be the smaller one. Okay, so let us consider, for the same algorithm, let us consider the number of frames is equal to 4. Number of frames are 4. And we'll check whether they are, that is the number of page faults are reduced or not. So here that number of frames allocated are 4. So first 1 is loaded, and then 2 is not available, so 2 is loaded here, and then 3 is not available, but new frame is, empty frame is there, so 3 is loaded, and 4 is not available, so 4 is loaded in the new frame or empty frame. And then this process want to access page number 1, 1 is already there, then page it wants to access page number 2, 2 is also there, so it will directly access them. Then it wants to access 5, 5 is not available, so it has to go for page replacement, it has to select a page for replacement. So among these 4 pages, the first entered page is 1, so 1 is selected as a victim page. So here in that place we can load page number 5, and then it wants to access 1. 1 is already replaced, is removed from this frames, so we have to find the victim frame. So victim page is 2, because this is first entered when compared to these 4 pages. So here 2 is replaced with 1. 2 is replaced with 1. Now we want to access 2, but 2 is not available here, so we have to go for page replacement. And among these 4 pages, the first entered page is 3. So 5, 1, 3 is replaced with 2 and 4. Next we want to access 3, but 3 is not available here, so we have to go for page replacement. Among these 4, first entered is page number 4. So it is selected as a victim frame, and here that 3 is loaded, and 5 is already there, so it will directly access it. Let us calculate their page faults. 1, 2, 3, 4, 5, 6, 7, 8. So 8 page faults are occurred. So if the number of frames are increased, then definitely number of page faults will become reduced. So for 3 frames the page fault occur is 9, but for 4 frames the page faults occurred are 8. But sometimes if the number of frames are increased, the number of page faults will also be increased. That effect is called Bilady's anomaly. It is called Bilady's anomaly. Bilady's anomaly effect. That is, if the number of frames are increased, then the number of page faults will also be increased, but it is very rare case. Next we will move to, so for FIFO, number of page faults are, for 4 frames number of page faults are 8. For 4 frames number of page faults are 8. Let us move to next one, optimal page replacement algorithm. Optimal page replacement algorithm. So in the optimal page replacement algorithm, a page which will not be used for longest period of time is selected as a victim page. One, 2, 3, 4, 5. A page which will not be used for longest period of time is selected as a victim page. So let us assume the number of frames allocated is 4. For all the remaining examples, so let us consider the number of frames allocated as 4. 1, 2, 3, 4. So here in the first page, frame, first page is loaded. So this is the first page fault. Then it will try to access page number 2. Page number 2 is not available. So it will send a page fault message to operating system. Operating system will find that new frame, and here it is loaded. Then next it is trying to access page 3, which is also not available in physical memory or here in the frames. So it will identify the new frame, and here it is loaded. Then it is trying to access 4. 4 is also not available. So 4 is loaded into the physical memory in the 4th frame. And now it is going to access frame number, page number 1. So 1 is already there, so no problem. Then it is trying to access 2. 2 is also there, and it is trying to access 5. 5 is not available here in the 4 frames, so it has to go for page replacement. So here the condition is select a page which will not be used for longest period of time. So here among these 4, which page will not be used for longest period of time? So here we are going to place 5 here. After accessing 5, very shortly we will be using page number 1. So we cannot replace 1, and then after that we will be accessing 2. So we cannot prefer 2 as a victim page, and then we will be accessing 3. After that only we will be accessing 4. So among these 4 pages, the 4th page is will not be used for longest period of time. So this will be selected as a victim page. So in that location you load, or in that frame load 5. So 4 is replaced with 5. The next 1 is there, next page is 2, 2 is also there, then 3 is also there, and then 4, it wants to access 4, 4 is not available in physical memory, so go for page replacement. So here after 4 it will access only 1 page 5. So we can prefer any one of the page among that 3 as a victim page. So I am considering 1 as a victim page. So 1 is replaced with 4. Next page it trying to access is 5. 5 is already available here. So the total number of page faults occurred here is 1, 2, 3, 4, 5, 6. Page faults are only 6. Six page faults are occur for optimal page replacement algorithm. The next, let us move to LRU. So LRU is nothing but least recently used. So in least recently used algorithm, we have to select a victim page which has not been used for longest period of time. Here in optimal, we have decided that victim page based on that future information, but in the LRU we have to decide, we have to select the victim page based on the past information or previous information. So LRU, for optimal algorithm, the number of page faults arrived as 6 for 4 frames. And LRU, let us consider the same example: 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, and then 5. So that the frames allocated are 4 here. 1, 2, 3, 4. I already told you we have to select a victim page that has not been used for longest period of time. So first time that a program will try to access page number 1. 1 is not available here, so it will send a page fault message to operating system. So operating system will bring this page into this particular frame. Then page number 2 is also loaded like this. Then page number 3 is loaded in 3rd frame. Then it will try to access page number 4. So 4 is not available here, but a free frame is there. So in the free frame 4 is loaded, and then it will access 1. 1 is already there, and 2, then 2 is also there. Now it wants to access page number 5. 5 is not available, so it has to go for page replacement. So here in LRU, it has to select the victim page based on the previous information, a page which has not been used for longest period of time. So among these 4, we have to find the place for 5. So before accessing 5, it used 2. So 2 cannot be used as a victim page. Then before that it accessed 1. So 1 cannot be used as a selected as a victim page. Then before that it accessed 4. So 4 is also not used as a or selected as a victim page. So definitely 3 is selected as a victim page. So 3 is replaced with 5 here. And then it tried to access 1 is there, and the next page is 2 is also there. Now it wants to access 3 is not available here, so it has to select the victim page. So before accessing 3, just now it accessed 2, so 2 is not a victim page. Before that it accessed 1, before that it accessed 5. So all these 3 pages are not the victim pages. So 4 is selected as a victim page. So 4 is replaced with 3. 4 is replaced with 3. And now we want to access 4. 4 is not available here, so we have to go for page replacement. And here just now we accessed 3, so 3 is not a victim page. Then before that we accessed 2 is not a victim page. Then 1 is also not a victim page. So 5 is a victim page. So replace 5 with 4. Next we want to access 5, but 5 is not available here, so go for page replacement. We just now we accessed 4, so 4 is not a victim page. 4 is not a victim page. Then before that we access 3, before that we access 2. So these 3 pages are not the victim pages. So 1 is selected as a victim page and 1 is replaced with 5 here. So the total number of page faults occurred are 4, 5, 6, 7, 8. So 8 page faults are occurred. So for LRU, the total number of page faults occurred is 8. So among these 3 algorithms, that optimal page replacement algorithm produce less number of page faults. So in general, that optimal will produce best results, but that the performance of FIFO and LRU will be changed. That is, sometimes it may be same, sometimes FIFO will give less number of page faults than LRU, and sometimes LRU is better than FIFO, but this is based on the way in which we are accessing the pages. But in general, that optimal algorithm is producing better results. So implementing this LRU is very simple. LRU, least recently used algorithm, this can be implemented in 2 ways. One is by using counters, by including counter values, and the next one is by including stack, by maintaining a stack. So counter means with each and every page table or with each and every page, with every page, let us associate a counter, let us include a counter. So with every page a counter is included, and whenever a page is loaded into the physical memory, then or whenever a page is accessed by the program, immediately its counter value is updated with the current clock value. So if we go for page replacement, a page with the minimum clock value is selected as a victim page. So the implementing that LRU by using counters is very simple. The next one is stack. We can maintain a stack. Suppose the number of frames given here allocated for a particular program is 4, we can maintain a stack with 4 elements. We can maintain a stack with 4 elements, and whenever a new page is loaded into the physical memory or whenever we access a particular page, that page should be available in the top of the stack. Top of the stack. Suppose in this example, first we are trying to access page number 1. So page number 1 will be loaded in the top of the stack. The next we are accessing 2. So when we try to access 2, that 1 is placed here, and that 1 will be placed here, and then 2 will be now available at the top of the stack. And then next one is 3. So 3 means that 1 and 2 are loaded here, are placed here, and the page number 3 will become the top of the stack. Then next one is 4. So these 3 will be placed here and 4 will be placed in the top of the stack. And then next page is 1. So 1 is there here. So now it is going to access 1. So 1 should be removed from this particular location and it should be placed here in the top of the stack. We can easily write like this. So in this way, that a currently accessing page or accessed page always be in the top of the stack. So by using this stack, we can easily select the victim page, a page which is available far away from the top of the stack is selected as a victim page. So here 2 will become the victim page. The next one is LRU approximation. In LRU approximations algorithm, along with that page table entry, it uses 2 more fields, 2 more columns. One is called modify bit and another one is called reference bit. 2 columns are maintained for each and every page, modify bit and then reference bit. So they both are having 1 bit information. Suppose page 1. Suppose a particular page is modified in the physical memory means then its respective bit value is set to 1. If it is not modified, then its respective bit value is set to 0. Similarly, if a page is recently referred, then its respective bit is set to 1. Otherwise, if it is not referred recently, then its respective bit value is 0. So it can generate 4 combinations: 0, 0, then 0, 1, then 1, 0, then 1, 1. So that means this particular page is neither modified nor referred. Then this page is not modified but it is referred recently. That page is modified but it is not referred recently. And then here this one shows that a page is replaced as well, that is referred as well as modified. So we have to select a victim page. Among that 4 cases, this will be the best option for selecting the victim, because that page is not modified and not referred recently. So we can select this particular page as a victim page. Okay, if it is not modified as well as not referred. But we cannot select these type of pages. Suppose a particular page is modified during that process execution, it is simply not swapped out, or that page is not simply ignored. Before loading that new page into the physical memory, that modified page content should be loaded or content should be copied into that backing store in which it is originally stored. So it will take some time. So we cannot prefer these type of pages as a victim page. We have to select the pages like this. The last one is counting algorithm. So in counting based algorithm, there are 2 types of algorithms. One is LFU, least frequently used, and another one is most frequently used. least frequently used algorithm, and another one is most frequently used algorithm. In the least frequently used algorithm, as a page is selected as a victim which is least frequently used. Here the most frequently used page is selected as a victim page. So both can be implemented in a simple way. So we can simply include a counter along with each and every page. So here, if a counter value is included, attached with each and every page, whenever a page is accessed, its count value is incremented by 1. So here in LRU, a particular page with the lowest count value selected as a victim page, and here in most frequently, a particular page with the highest frequent value or highest count value selected as the victim page. So implementing this type of page replacement algorithms are very simple. So now we discussed different page replacement algorithms before: optimal, LRU approximations, and counting based algorithms. But among these five, these three algorithms are very important. But among these three, that optimal is producing better results than these two. But these two, their performance are based on the number of reference strings or the order in which we are accessing the pages. Then the last one is thrashing. So what is thrashing? During a process execution or a program or application execution, if the sufficient number of frames are not allocated, that operating system will spend more time for doing page faults than executing that particular process. That is the performance in overall that process execution time, that a program will spend more time for replacing pages and loading the pages into the physical memory than executing that particular process. So this situation is called thrashing. So if thrashing is occurred, then definitely the performance of the system will be degraded. So operating system is responsible for providing or allocating sufficient number of frames for each and every program which is going to be executed. Then only the performance of the system will be in stable state, or otherwise the performance of the system will be degraded due to this thrashing. And it has to avoid the thrashing problem, and then only that a degree of multiprogramming will also be maintained. So maintaining the performance of the system and maintaining the degree of multiprogramming is very important, and that can be done by the operating systems. So far we discussed that virtual memory concept, that virtual memory that includes demand paging. It can be implemented by using demand paging, and then demand paging, if a new frame is not available or any new frame is not available in the physical memory, then they have to go for page replacement. So we discussed different page replacement algorithms, and we told about thrashing, what is thrashing, and that thrashing should be eliminated or should be removed in the system to maintain that the system state in a as a stable one. Thank you.